like to thank you everyone for being here today. So I am Quang Hui. I'm the Vietnamese student in Department of Mechanical System Design and Engineering. So in my academic advisor is Professor Chu here. So I'm here today to present to you about the topic of the radio steering interferometer for aspheric surface testing. I divided my presentation into the 5 main parts. The first is the introduction. The second part is the principle. The third part is the simulation. The next part is the general experiment and analysis. And the final part is the conclusion. Let me talk about the introduction. So we are living in the world of the technology, the world of the non-stop change. The world keeps moving. So all of the smart devices will be happen in the life. So as you know that the smartphone, they want to focus on the user experience. So the next generation of the smartphone will be updated day by day. So this is a camera system. So the requirement of the complex camera system is needed to reduce the size, reduce the thickness of that. Not only for the spherical surface, but also the aspheric surface. The aspheric surface still now is the challenge for any optical engineering and any researcher, with the requirement for the high resolution to fabricate and measurement. The problem is we have to fabricate machine with high precision for fabricate and measure it. This is the machine. It's a DTM machine. DTM means dynamic turning machine. This is a machine, so that's a project, the high precision processing system for high uniform manufacturing of ultra small optical lenses. Let me talk briefly about this machine. What we have to do. We need the system design, the environment control, the manufacture system, the injection modeling, the package alignment, and the keys, and the most important, focus on the ultra precision technology. So the machining processing with the requirement of the shape accuracy is 100 nanometer, the surface rounding around 10 nanometer. So the interactive cam, user-based interactive technology. Combined with the machining processing, so we have to check that surface by the profile metrology. It might have applied into our machine with the sharp accuracy 25 nanometer IMS. My effort in that project focus on the profile metrology. Then I taught some methods of the surface testing. This is the contact measurement. This is the stylet method. So the stylet will be touched on the surface. We get the 2D diagram of the surface by move back from the top, from this side and this side. To get the 3D profile, we have to move back and forth the stylet. It is time consuming to measure the target. So it is an example of the contact measurement in the FTS from tally surface with the precision of 16 nanometers. So it is the other example, UA3P around the 0.1 micrometers precision. The result in that method is that the surface deconstruction. To avoid the surface deconstruction, it is a non-contact measurement. This is the other method to measure the surface, the focal sensor. This kind of sensor, based on the focal point of the laser, depend on the lens system and the distance between the lens to the target, it will be detect the surface. Similar to that method also have to the scanning 2D, move back and forth to get a 3D measurement. It's a time consuming. So to get the 3D method is a famous method. To work on there is a Hartmann sensor. The Hartmann sensor is the can-wave hit to the target and detect by CCD. So this is the special case of the CCD. This is the design. In front of each pixel has one lens. We call this one is the lenses array. Normally, in here is a can wave. The principle of the Hartmann sensor, if in here is a can wave, the focal point hit in the center of that pixel. However, Normally, as you know, that the wavefront always include the operation. So in here, the wavefront missing at the center. If the point look like in this way. By using the slope, we can reconstruct the 3D target profile. The precision of that method can be hit up to the 20 nanometer. So the disadvantage of that method about the cost is very high and the low lateral resolution. The interferometer in optical testing know that the best way to test surface. So this is the traditional method, Twyman green interferometer, for testing the spherical mirror. The plateway in here is split into two arms, the reference mirror and the other arm via the diverse lens to make the spherical wavefront and fit with the spherical mirror. Two of it overlap and overlap each other in the CCD on here and get the interferogram. This is a clearly fringe because of the point spacing between the dot and prime is very clear. It is easy to reconstruct the 3D profile measurement and keep the high accuracy for that method. However, if we apply the traditional method for aspheric testing, it will be a problem. The reference arm is skipped. The spherical wavefront have to fit with the aspheric surface. It's happen for the operation. So here the reference wavefront and the operation is the red one from here. So the difference between that the reference wavefront and the test wavefront, we call that one the departure. And when the departure is very high, we will get the very dense fringe. With this kind of fringe, we cannot reconstruct the surface. In this study, we propose that the radial series interferometer combined with the dynamic interferometer. With the advantage of the dynamic interferometers, we can get the single shot 3D profile measurement to remove too much of the vibration in the industrial. So, with the characteristic reference free of the radial series interferometer, we can reduce too much of the departure. Is here. This is a very low cost to develop the high accuracy of the system to aspheric testing we propose in that study. So let me talk detail about the principle of that method. This is the wavefront under test. This is the linear polarization, linear polarizer. This is a beam splitter, polarizing beam splitter, and rectangular one is a radial series interferometer. The wave under test will be defined the polarization state by using the linear polarization. Test plate at 45 degrees. The beam splitter will be split into two arms based on the polarization state. This is the reason why we have to put the linear polarization at the 45 degrees, because we want to make the two split beam at the same power, at the same intensity. Let's focus on the blue part. The wavefront under test will be defined the polarization state at the 45 degrees and transmitted via the polarizing beam splitter, and in here is the horizontal linearly polarization and passing through the lens 2, lens 1 respectively, and one more time transmitted in the PBS. Similar to this in the red part, the 45 linear polarization state will be reflected in the polarizing beam splitter and transmitted in the lens 1, lens 2 respectively, and one more time reflected at polarizing beam splitter and going out is an interferometer. Because of the difference between two focal length of that two length is 100 and 101.6 is the difference. So we have to the two side of beam. This side beam and this side beam is identical. However, because of the length 2 is less than length 1, so this one is larger than the initial. So in here, so the length 1 is greater than length 2. So in here is less than the initial. So this is the two beam for magnification. We call this one the magnification, and here is the demagnification and the red one. In the output of the interferometer, we have the orthogonal polarization stage. So we put the parallel plate at 45 degrees in here. This means that the parallel plate will be convert the linear polarization state to the circular polarization in here, and two of it overlap in CCD. The magnification part overlap with the demodification part and make the interferometer in the overlap area. Let me talk detail by mathematics, geometric expression. So as I described before, the blue one will be transmitted, or the beam splitter, in this direction. So here is a linear polarization of 45 degrees. It's represented by this zone matrix. Around this arm is the horizontal polarization state. So P at 90 degrees is represented by this matrix. If the quarter plate must take place at the 45 degrees, it represented by this matrix. And about the random polarization state for the waveform of the test, it is a zone vector. So multiply by all of it, we get this kind of vector. So this vector in zone matrix, so we get the left circular polarization. Similar to the red part, just replace the P of 90 degree by the P of the 0 degree. So the red one is reflected in the PBS. So I prepared that one compared with this. And this is the result for the red part. This vector represents for the right circular polarization. So in modification part and demodification part, we get the left circular polarization and right circular polarization. It is a material for the dynamic interferometer. In dynamic interferometer is nothing but it's a special design camera. In front of the camera, they mark on the polarization, a polarizer at angle alpha. This is an interferogram touched in the CCD. If the polarization state, polarization angle is alpha, the phase shift value is the 2 alpha. In design of the cameras, so they make linear polarizer at the 0, 45 degree, 90 degree, and 135 degree, and we get the phase shift. That's a 0, 90 degree, 180 degree, 270 degree, respectively. This is the two results for 4 interferogram, I1, I2, I3, and I4. So the mathematics represent for 4 interferogram I take is I1, I2, I3, I4 with a different phase at 90 degree. Apply the 4-bracket algorithm. I substitute between that the I4 and I2, I1 and I3. So we get the phase. The phase is I1. The phase is in here. So it's the initial phase by takes arctangent for the ratio between that two. This is the unwrapped phase at one point, at the X pixel of the CCD. To get the full area of this, I take that equation for all of the pixels in the CCD. It is a result. The advantage of dynamic interferometer is the single shot measurement. We can simultaneous. In the one shot, we can get the 4 interferogram. This is a rapid phase. Here is a cross section. So the arctangent return the value from the minus pi to pi. So it is a discontinuous phase. So as I talked in the 2D diagram, here is a discontinuous phase. So we have to convert from a discontinuous phase to the continuous phase. It means that this point should be matched. This point should be identical. So convert from this to this in the linear phase continuously. This is an unwrapping process. The unwrapping process is nothing but just subtract or adding the 2 pi for each period of time. So the phase map will be scanned vertical and horizontal direction. So we get this kind of phase. It's unwrapped phase. This is the target we have to measure in phase. In the next part, I want to talk about the simulation. This is a schematic of our measurement. This is the coordinate. We make the plane wave output. So the output plane wave in here, passing through the linear polarizer, and reflect at the PF, hit to the target, and come back again, transmitted in the BS, and passing through the RSI system, and detect by CCD. And the same configuration with this, we also measure for flat. The plane wave in here, hit to the flat, and reflected in here, and passing through passing through the RSI system. And using that configuration, we can measure the flood and aspect together. So to modeling this one, we using the software called like Zmax. Zmax is a software can be modeling between the surface to surface using the ray chain modeling. So this is the design of the collimator design. The collimator design is made on a Keplerian telescope. So the Keplerian telescope is nothing but just using the two positive lens to convert from the smaller can weigh in here to the larger can weigh in here, or inversely. So the key in here is the distance between that two positive lens. We have to optimize for that distance. We set the angular radius for this point and set this value for the variable and get the optimization distance. How can I know that value is good? I limit the aperture in the output like a 5.4 radius and set the float by stop sign. All of the spotlight contained inside the area radius, so it means that this kind of design collimator is very good. And this is the simulation for flat target. It is an object in that study. So it is a spec of the complex length mode target is aspect surface. So it's a radius and the 4 coefficient of the aspect surface. And here is a interprogram in simulation. So how can we know that the full aperture of the target can be measured? We can get is a real change data in here. So this data provide for that we can hit full aperture of the target. In the next part, I will talk about the experiment and data analysis. As I described before about the collimator, so the design, the key technique is the distance between that two lenses. And we set up the mechanical design for this, follow in that distance. And I limit the aperture around the 5.4 radius. And in here, I use using the iris to limit that. The last one we're using in that system with the center wavelength at the 830 nanometer. With the full width maximum at the 20 nanometer range. This is the experiment setup. As I did right before about the schematic, we set up the experiment follow this. The collimator, 40 mirror in here, and one arm hitting the flat, one arm reflected in the BS, hitting the target, aspect target, and two of it passing through the RSI system and detected by CCD. This is the aspect result. So here is the experiment result, and here is the simulation result I described before. So in here, the shape of the experiment and simulation is agreement. This is dot, prime, dot, prime, dot. It's the same like this. Dot, prime, dot, prime, dot. This is the flow chart for data analysis. From the experiment data and simulation data I just compared before, it starts together. So experiment data will get the rapid phase via the forward algorithm. And via the unwrapping process, we get the unwrapped phase. And remove some unexpected term, we get the procession for this data. So in simulation data, we get the 2D interprogram. And the 2D interprogram and the center of the cross section will be compared directly in the optimization process. We will apply the optimization process for the two steps. The first step is the flood measurement to calibration of the system. The second step is the aspect measurement. This is the result for the aspect measurement analysis. So it is the forward fringing we get in the CCD. Via the forward catch algorithm, so we get the rapid phase around this. And in this phase is the unexpected data. So we will get rid of it by masking. And via the unwrapping process, we get the unwrapped phase in here. So I sampling for this one by remove some unexpected term like piston and tilt. So we get the symmetric mark and get the 2D cross section. And in the simulation interprogram, so I get the 2D of it, and this is the red one. I compare directly between the red one and blue one in optimization process. So optimization process is nothing but we keep for the experiment data and change the simulation data to hit the identical between the simulation and experiment. In the loop parts, each will be fixed by using the calibration by flat. And this is the P6 is the distance between the focusing length to the BS. The P7 is the distance between the focusing length to the target. So the two parameters will be input of the optimization process. However, we cannot show that the aspect target is correct or not, if the perfect or not, so we have to put more for the aspect coefficient, aspect radius, and for aspect coefficient to the input of the optimization process. It means that I will change that number, and find that number. The input of the optimization process for aspect is the 7 parameter. So this is the result. In the initial situation, so if 2 of it is not fit, so at the optimization process, so 2 of it is a very, very good data. So by using the changing of that parameter, so we use the red one, we can get the red one, and after that we can reconstruct the surface, and this is a surface reconstruct and compare it with IEA page. 2 of it is almost overlap, but in the subtract between that two is the error of that system. The PV hit around the 32.2 nanometer and the IMS around the 10 nanometer. So the final part is conclusion. As I talked about some first line, so the requirement for the machine in our effort in the profile methodology, it's applying all machine with set accuracy in 25 nanometers. So the result for the measurement, we hit to the IMS error around the 10 nanometer. So it let down the requirement in the project. So in the radio sharing interferometers, so it's a low cost to develop the system to get this high accuracy I described before. By single shot measurement, 3D profile measurement using the dynamic interferometer, so we can get the profile just only single shot and surface non-deconstruction. And we will apply our system in the DTM machine. This is the DTM machine. And about the next step, we will apply our system measure directly in our machine. We have to fit this one with this kind of machine. And here is our system. It is near to measure the target in here. We get the result directly in our machine. And this is the next step for my project. So everything about my thesis I already described. Thank you for listening.